So we were asked to raise our hands at the start of the previous talk to say what our background was. I went with psychologist. I think I'm kind of a bad psychologist, a bad neuroscientist, bad physicist, definitely. And so this talk is going to be a reflection of all of those bad things, but hopefully we'll cover quite a bit of ground. So I'm going to tell a funny story about the brain, completely unvalidated. And the story that I'm going to tell is about some of my efforts in recent years to try and understand the development of social behaviour in rodents in particular through computational modelling. So the question that I'm really interested in, what this is all getting at, is how early experiences shape the developing brain. I hope everyone here would agree that early experiences do shape the brain. And if you were to open a social psychology textbook, somewhere there would be a description of this classic work from the 1950s by Harlow and colleagues, where what they did is they took these little monkeys, so very infant monkeys, and they gave them the opportunity to cuddle up with two different surrogate caregivers, right? So the one on the left looks nothing like mum, but delivers food. Okay, so this surrogate caregiver satisfies some kind of basic needs for the infant, but it's only very basic. It's delivery of food. Whereas this terry cloth monkey or surrogate caregiver dummy monkey on the right looks and feels a little bit more like mum, but doesn't deliver food. And the interesting outcome of these experiments was that the infant monkeys would choose to cuddle up with the soft surrogate mother that doesn't deliver food, and not to cuddle up with this thing here which does deliver food. So on some level, it seems as though the infants are more happy to interact with a caregiver which resembles mum in some more qualitative way, and it's not just about the delivery of this primal need for food. And so lots of textbooks will summarize this, and social psychology, around which the idea of attachment theory has grown, refer back to this work as important, because the infants that had the opportunity to cuddle up with the soft thing here also grew up into well-adjusted monkeys, right? So they were securely attached in the language of attachment theory. They were less distressed when left to their own devices. They grew up to be less aggressive and so on. And so this is classic sort of basis for what later became attachment theory. Attachment theory is very important in social psychology. What you don't see in the social psychology textbooks, typically, is the observation that was made by the original authors, which is that these effects only work. The infant is only drawn to the object on the right if the object is also heated. Okay, so not only does the thing have to be soft to touch, but it also has to be warm, and most people forget about that. But this has been picked up more recently by some social psychologists, Ijerman and so on, who have drawn attention to the fact to how important warmth is for mammals, including primates and humans, for shaping these early interactions between an infant and a caregiver, and how they then shape the later development of the personality of the animals. Okay, so they highlight this idea of this theory of social thermoregulation. So in their words, the most basic function of social thermoregulation is to help warm other agents by coming into contact with them. And their idea is that these higher level sort of psychological phenomena like attachment, social emotional functioning, and affect regulation and so on, the things that social psychologists are interested in, are sort of scaffolded on top of these more basic, primitive behaviours which are around heating one another up where that's an available option. They continue that that they draw a distinction between these kind of low-level systems for social thermoregulation, which is reflected in these kind of behaviours that you see in animals like penguins, which are birds, which are also endotherms, which also need to maintain a high body temperature to stay alive. These kind of reactive behaviours of just cuddling up with one another, versus these sort of higher level behaviours around social thermoregulation, which are about predicting the thermal consequences of coming into contact with another agent, another conspecific. And so they think that that these levels of social thermoregulation are reflected in the organisation of behaviour and in the organisation of the brain in terms of bioenergetic costs. Okay, this will become important later on. Another nice example of social thermoregulation, which I'm going to concentrate on in this talk, is huddling behaviours in juvenile mice or infant mice and other rodents. And this is essentially all that infant rodents do for the first 3 weeks of life, whilst the brain is most plastic and wiring itself up. And so in the words of India Morrison, she has this idea that the mammalian brain has evolved these kind of neural shortcuts that are useful for predicting the thermal consequences of coming into contact with another agent, that no longer require the sort of full cycle of coming into contact, being rewarded by the thermal exchange that contact brings, and so on. But that in particular, she's interested in how affective touch signals, so sort of soft touches, which are correlated with the delivery of thermal reward, how those are represented in the brain. And lots of people are now thinking that for the mammalian brain in particular, this relationship between soft touch and the warmth that is typically brought about by soft touch are shaping the neural circuits that are involved in representing these higher level psychological phenomena like attachment and emotion regulation and so on. Okay, so so this is fun, right? Because there's the potential to think about thermal physiology and heat flowing and being exchanged between animals, and to then bridge the gap between an understanding of that the physiology involved to these higher level psychological ideas that relate early experience to the development of attachments and personality and so on. So what we need to do to sort of exploit that potential for understanding psychology in terms of the underlying physiology is to identify a good model system. And this is the model system that I've been very interested in. It's also an incredibly sweet video where we see a litter of, I think, 5-day-old rat pups filmed by Robin Grant at Manchester Met when she was doing a PhD in Sheffield. And as I said, this is essentially all that these animals, our most important models in neuroscience, rodents, this is all they do for the first 3 weeks. They sort of squirm and fight for the best position where they're going to get the most thermal reward and compete, and some also cooperate and compete with one another for the best position until they end up flipping each other over. They do that, and then occasionally they'll scramble over to mum, they'll get some milk, and then she'll collect them together, and they'll keep doing this over and over again. Whilst this is happening, their motor skills are being trained. They're learning, in my view, they're learning correlational structure between patterns of sensory input that are coming in and the consequences of the motor actions that they make. They're learning that when I hear a squeaking pup over here and I subsequently get bashed on the right-hand side of my body, that's coupled with an optic flow from the right to the left. So they're learning all of these wonderful sensory and motor correlations in the process. As I said, during the first 3 weeks, whilst the brain is most plastic, and certainly whilst cortical circuits are still wiring themselves up. Okay. So there's been lots of work on huddling as a model system, lots of it due to somebody called Jeff Alberts at Indiana University. And this is a sort of classic study which relates back to those Harlow experiments, where what they did is paired, they had sort of surrogate objects in an environment, either a warm tube or a tube which wasn't warm, a tube about the same size as the pup. And they paired the experience of either the warm thing or the control thing with different odours, and then tested the animals when they were adults to see which objects the animals would spend, or which scent of the object the animal would spend most time in contact with. And what they find, as you might expect, is that if you pair a novel odour with the early experience of a warm object in an otherwise cold environment, then when you expose just that odour to the animal when it grows up, they will spend more time huddling and maintaining close contact with it. So this gives us a kind of idea that the animals are using thermotactile stimulation as a mechanism for some sort of classical conditioning, in this case, odour heat conditioning. Sorry. Yes?
What's the difference between odour A and B?
They were two arbitrarily chosen novel odours, so maybe like peppermint and banana. So they're just showing the control that the odour itself doesn't matter. Okay. So a little bit more motivation for studying huddling. So this is a much later study. There are lots of studies of a similar kind of flavour to this one. I've just chosen this because I like it. If you characterise the pups in the litter based on the position that they typically occupy, so they're either typically in the centre, C, somewhere intermediate, or at the periphery. So you go through and you characterise the pups. You say, are you a central pup? Are you a peripheral pup? And then you present the animals when they grow up with a scenario in which they have a gap to jump, and across the other side of the gap is played over a speaker the sound of a distressed littermate. So they make these sort of ultrasonic vocalizations. Then you look at how willing the animal is to jump over the gap to go and attend to the cries of the littermate. You find that there's a relationship between the animals which typically occupy the centre versus the periphery of the huddle as pups, and how pro-social they are when tested later as adults. And in these experiments, these were done very nicely. They controlled for some of the possible confounds there, such as whether it was the animal was the runt of the litter, by cross-fostering the pups, so they were matched in terms of their weight. So these were animals tested at days 19 to 23. Okay, so hopefully we can agree that there's some potential interest in understanding. If we can understand what's going on in the huddle, then maybe we can start to model this relationship between early experience and later development. Okay, so what I want to try, and I don't care whether you believe the models or not. This is an unvalidated talk. But the sort of take-home messages that I want to leave you with, and I'll return to these at the end, this idea of social thermoregulation is a bridge between psychology and physiology through behaviour. That huddling in rodents in particular is a natural behaviour which is important for developing animals. And it allows us to potentially investigate this relationship between psychology and physiology empirically. That also we, by modelling huddling behaviour, particularly modelling the physiology, we can generate testable hypotheses that relate that behaviour to the underlying cognitive architectures for social behaviour that might be involved in social behaviour. And towards the end, I'll try and show you my way of trying to get a handle on this by this idea of sort of reactive thermal behaviours serving as a sort of scaffold or a basis for which higher level ideas that involve predictive behaviours can form around. And I'll try and keep in mind that brains, we should all remember this, brains are about moving bodies, and that relationship between the brain, the body, and the environment in which it plays out is all done and has evolved under the constraints of minimizing metabolic costs of behavior, however those might be defined. Okay, so a really cool thing, so we're trying to now understand the physiology that's related to this physiological huddling behavior. And a really nice aspect of this system is that you can, in some sense, you can measure the energetic costs which are being expended by the individuals when they participate. You can stick a thermal camera over them and you can see that in a cold environment, the animals are spending a certain amount of energy to keep their nice 37-degree body temperature going, and that energy, some of that energy is conserved when they huddle together. Okay, so you can think on some level of these pups as being little radiating heat sources that might be motivated to come together and form groups. And I'll just point out that on this little pup here, you can see a sort of warmer spot just above between the shoulders. That's the warmth that's generated by brown adipose fat tissue, which is one of the major things that the infants and the adults as well have to generate their own heat, and that will become important for some of the models. Okay. So a crucial starting point for modelling this stuff is Newton's law of cooling. This is really simple. This says that if an animal or an object is to maintain a temperature, Tb, a discrepancy between its own temperature, Tb, and the temperature of the environment external to it, Ta, Ta for ambient, then it needs to generate this amount of energy, G, or this amount of heat, and that is affected by C, which is the thermal conductance of the body, and also A, which is the amount of, or the proportion of the body surface which is exposed to the ambient temperature Ta. Okay, so this is sort of some basic physics, and there have been lots of kind of experimental validation, so this is a sensible way of describing some of the high-level thermal properties of animals. So here's a couple of examples showing that if you pack animals into groups of different sizes, increasing size along the x-axis, then the amount of heat that they generate by thermogenesis, which is equivalent to this thing G, decreases in proportion to their thermal conductance C. So the slope of those lines gives an indication of the thermal conductance, and these experiments show some manipulations to the thermal conductance of the animal, such as breeding a species which doesn't have hair and therefore doesn't have as much insulation. Okay, so Newton's law of cooling is a good starting point for us. An important concept is also this thing called the thermoneutral zone, which has been extremely well characterized for mice and rats. You can draw an equivalent relationship for other mammals, including ourselves. So if you look at for different ambient temperatures, TA, you look at the thermal output, in this case for some different systems. So this is skin blood flow, this is evaporative water loss, and MR is metabolic rate. That's equivalent to our G, our thermogenesis term from Newton's law of cooling. Then what you find is that there's a really, the slope of this line here is C, that's the thermal conductance, that's how biologists would work it out. And animals also have, as we do, the thermoneutral zone, which is a range of ambient temperatures over which the animals can maintain a stable body temperature, so 37 degrees, without expending more energy than they get away with from their basal metabolic rate. Okay, so when the animal's at rest, when you stray outside of this thermoneutral zone, the animal is having to do some work in terms of burning fat or shivering the muscles in order to thermoregulate at 37 degrees. If it gets too hot, the animal has to do some active work to cool down, such as panting or sweating for us. Okay, so the thermoneutral zone is the happy place, right? That's where the animals want to be. And that's where we want to be as well. So we experience discomfort when we fall outside of those ranges. So how do we maintain this thermoneutral zone? We've got, animals have various physiological things that they can do about it. So that we can either burn fat, which involves metabolism, and increases the metabolic rate, increases oxygen consumption, is very expensive. If it gets much colder, then we can start to shiver, so we contract the skeletal muscles. So this is expensive, this is extremely expensive. Dilating and constricting the blood vessels is not expensive. Okay, so this is passive physiological thermoregulation. It doesn't cost anything. And essentially what happens is that we maintain our basal metabolism here by doing constricting the blood vessels. When we get too cold, we start to burn fat. When we get even colder, we start to shiver. And like I said, we do sweating and panting when it gets cold. And so these things are all under the control of the hypothalamus. Okay? And specifically, the sort of input, if you like, input structure is the POA, the preoptic area of the hypothalamus, which then regulates what's going in VTA and periaqueductal grey, and controls the signal that's going through the Rafe nucleus, and then eventually to these different thermal effectors. Okay, so the hypothalamus and the preoptic area of the hypothalamus in particular is kind of in charge of all of this. Okay, so how does that work? The information comes from the skin, from thermal sensors. It goes up the spine, where it, through a couple of synapses, where it converges on the preoptic neurons of the preoptic area. And when you measure from neurons in the preoptic area, there are two broad classes of neurons. There are warm sensitive neurons whose firing rate increases more or less linearly with the temperature that's sensed to the skin. And there are temperature insensitive neurons which don't care about the temperature. They're just firing away tonically. And people have described for a long time, have described a basic kind of circuitry of how that system of warm sensitive and temperature insensitive neurons come together and produce some control over the output. The basic idea is that warm sensitive neurons, they're firing away in proportion to the temperature sense of the skin. If they excite a neuron and that neuron has some inhibition from a tonically active temperature insensitive neuron, then the net effect is that the output of this neuron will be nothing until some threshold is met, until the firing rate from the warm sensitive neurons overcomes the tonic inhibition from the insensitive neurons. And you can wire up the circuit in the opposite way with warm sensitive neurons inhibiting and tonic temperature insensitive neurons exciting, and you'll get the opposite profile of an output here. So you'll have the opposite thing, right? Which you could connect to a cooling system, to a heating system here to increase the muscle contractions or the fat metabolism as the temperature gets cold, or in this case to increase active cooling mechanisms when the temperature gets too hot. Okay, so we can represent that in an extremely simple, even cartoon-like model where we imagine different versions of that circuit coming on for different set point temperatures, right? So we might have a sigmoid or even a simple sort of piecewise thing here where muscle shivering comes on for the largest discrepancy between the preferred body temperature and the actual body temperature here. As you get a bit closer to the preferred body temperature, fat metabolism comes on. Blood flow is regulated somewhere in the middle for temperatures which are near the preferred temperature of 37 degrees, and these active cooling mechanisms come on for higher temperatures. Okay, now we can also build very simple models of how the thermal dynamics of the animal look. Okay, so we can define a skin temperature, which we can write a differential equation here to describe how the temperature of the skin changes over time. The skin temperature is pushed towards the body temperature and is also pushed, so it's pushed towards the body temperature at a rate which is given by alpha, in this case representing skin blood flow, and it's also pushed towards the ambient temperature at a rate which is determined by A, the exposed surface area of the animal. And we can come up with a similar description for how the body temperature changes over time. So the body temperature will decay towards the skin temperature at a rate given by the skin blood flow. When these internal mechanisms of heating and cooling come about, they contribute to the body temperature directly. So Q here is representing the combination of the basal metabolic rate, GB, the heat which is generated by burning fat, the heat which is generated by contracting the muscles, and subtracting the heat which is lost through active cooling mechanisms. Okay, so we can build a simple model of the dynamics and we can run it and see what happens. And just to show you the basic idea, in this model, we imagine that the ambient temperature drops at some point, and what that shows you is that the skin temperature in green will start to decay towards the ambient temperature, but when these different thermal effectors come on to compensate, the body temperature remains relatively constant. Okay. Now the nice thing about having this idea of the thermoneutral zone is it allows us to place constraints on a model like this. Okay, so what we can do is, so the dashed lines here are sort of what we would hope to achieve. So these are constraints which are placed on the model. The blue line here is the outcome of that model after exposing it to different ambient temperatures. And what we can do is we can relate the, we can take constraints from the literature, such as the fact that the basal metabolic rate, GB, is known to be allometrically related to the body mass, M, and that allows us to put some units on some of these quantities, so kilograms and watts and so on. And we can impose a constraint that the preferred temperature should be 37 degrees. If we do that, then we can define certain properties on this graph, which place constraints on the free parameters of the model, so K1, K2, and K3, need to be combined in a certain way in order to be compatible with observations about what is known to be the lower limit, TL, of the thermoneutral zone. Once we have choices of these parameters which give us a realistic lower limit of the thermoneutral zone, so lower temperature here, that can then be used to calibrate the slope of this line, which gives the thermal conductance in terms of these parameters. And once, and it's known that the thermal conductance, the relationship between the thermal conductance and the body mass is known for mice. So we can use that to then place some constraints on these other model parameters, and that's what we end up with here. So don't worry about those symbols. The point is that we can use the thermoneutral zone and these well-known relationships between the body mass and metabolic rate, the body mass and thermal conductance, to place constraints on what the aspects of this dynamic model should look like. And when we do that, and we run it through the simulation, we can then get relationships between the thermal effector responses and now the ambient temperature, which you don't know in advance of running the model. And we can try and draw comparisons and calibrate to the data from the thermoneutral zone. And importantly, we can start to then come up with a description in a formal sense of the motivation that the animal has to change its thermal situation. Okay, so if the animal is straying outside of the thermoneutral zone, it's using energy through muscle contractions, it's using energy through fat metabolism, and it's using energy to do active cooling. The combination of those three things might be some kind of proxy for how motivated the animal is to do something about its thermal situation. Okay. Okay, so this is a good setup for the huddling model. So what I've been doing over the years is then trying to use some of these constraints to then tie the thermal physiology to the social behavior. So we can look at, take data from studies of huddling where people have looked, simply put animals, litters of different sizes, into an environment and that's temperature controlled, and you can measure somehow quantify from the images how huddled, how grouped together the animals are. And as you might expect, when it's cold, the animals will huddle. Huddling level is high. And when it's warm, the animals will disperse, so huddling levels get low. And this has been described as this kind of S-shaped curve, which hopefully you can make out, has been described as a second-order phase transition for any of you with a sort of physics background. Okay, so this sort of S-shaped curve here. Now, what I did is I made a model which, starting with Newton's law of cooling, so G equals CA times TB minus TA, and you can rearrange that to come up with an expression for how the body temperature should change over time, and that represents this idea of the animals using their physiology, particularly these Gs here, to do something to control their body temperature. You can then ask, okay, given the best I can do physiologically and the discrepancy between my current body temperature and the preferred temperature that I want to maintain, how should I move around in my environment in order to thermoregulate? And if the animal is able to tell the difference between the temperature on its right and the temperature on its left, then we can come up with a simple expression that says how the animal should change its direction if it encounters other thermal stimuli in the environment. And then we can move, in a simple simulation, we can move the animal forwards in the direction which is facing, which it is chosen based on those constraints. And if there are any physicists here, you might recognize this as something called a VICSEC model. It's often used to model things like swarming and flocking behaviors. And then finally, we can factor in the amount of heat which is exchanged between animals when they come into contact. Okay? So as well as losing heat to the environment, when the animals come into contact, their body temperatures should converge to the temperatures of each other. Okay, so here's what the simulation looks like. So we've got a little simulation of, I think, 12 very, very simple rat pups controlled by the 3 equations on the previous slide. And what we're doing over time is we're increasing the ambient temperature. So we're taking TA and we're ramping it up very slowly. And what you see, hopefully you can see they're all huddled together because it starts off nice and cold. And then over time, as it heats up, their average body temperature of the group will increase over time. But their huddling stays at a high level, so they're as packed in as they possibly can be, and they can't do anything when they're down here about their low body temperature. That's the best they can do. But then at some point, as the temperature increases, you can hopefully see that the simulated pups will start to break up from one large huddle into smaller subgroups of huddled groups. So temperature's rising, and suddenly it switches from one large group to this kind of cycling where the size of the average group size is adjusting, or they're able to adjust the size of the groups that they're in order to thermoregulate. Okay? So it's an extremely simple 3 equations from the previous slide, and you get this nice emergent property of the group, which is the emergence of huddling, which follows something like this kind of S-shaped profile that's been observed experimentally. And but crucially, that it creates this kind of almost thermoneutral zone where the animals are able to adjust their interaction with one another in order to maintain the average body temperature of the group at a nice 37 degrees. When it gets too cold, they can't do anything about it. When it's too hot, they can't do anything about it. But this thermoneutral zone is defined by their social behaviour, if you like. How am I doing for time? Okay.
15 minutes left.
Brilliant. Okay. Okay, so here are those graphs, or those graphs plotted out a little bit more carefully. Huddling is high and goes to low. Average body temperature increases, but there's a sort of thermoneutral zone. And what's interesting is that if you look at the what I'm calling the PUT flow, which is just a standard deviation of the PUT positions, then you get this kind of spike in the PUT flow at the transition temperature between huddling and not huddling. Okay, and that's intuitively that's this observation that the sizes of the groups that they're in is changing very quickly around a very specific temperature. Okay, and this is something which has been observed in the literature, so it's called PUT flow by Jeff Alberts and so on. What we saw aspects of it in the movie at the start, where the pups they don't just stay aggregated in one giant mass, they cycle and flow from the centers to the edges and so on over time. And this model makes a prediction about that the PUT flow should have a very definite peak at the transition temperature of that phase transition between huddling when it's cold and not huddling when it's warm. And you can muck around with some of the algebra to define exactly how wide this thermoneutral zone should be as a consequence of the thermal properties of the individuals that make up the group. You can also start to ask questions based on an extremely simple description. Animals either turn to the left or to the right, depending on whether it's warmer on the left or the right, or whether they're currently too hot or too cold. You can try and distill that into some kind of minimal circuit diagram. And it turns out this kind of multiplication of two factors here, the minimal neural network which is required to implement this, corresponds to something that has to solve the XOR problem. And that suggests that there must be a minimum number of processing layers, which in turn can serve as a hypothesis about the basic structure of the neural circuitry which is required for implementing this particular kind of turning behavior. What I've been doing a bit more recently is then trying to make the model even simpler. It's always a good thing to make models simpler. And one way to do that is to make the observation that if we know the number of animals which are grouped together, n, then we can work out their exposed surface area because it's been observed in lots of experiments. Their average exposed surface area decays with the number of bodies which are collected together, and this exponent here has been estimated as -1/4. That means that if we know the number of animals that are grouped, we can say what their exposed surface area is, and therefore we can use Newton's cooling law to work out their body temperatures. If you can do that, then you can come up with a simpler model of huddling, where you imagine that the agents are no longer having to sort of wander around in a two-dimensional environment, but we can simply decide what's the probability that animals will either break off from the group's configuration that they're in to form a larger group or to form a smaller group. And you can do that through what's known as a Ising spin model in physics, where what we're interested in is determining the probability that that pups, once they come into contact, want to stay in contact with one another versus want to break off from one another. Okay, so we can define this parameter here based on the body temperature of two agents which have been chosen at random, and then we can make a decision about whether those animals should maintain contact or whether they should separate from one another based on this icing spin formalism. Okay, when you do that, what's interesting, that's 10 lines of code to simulate that, compared to 100 lines of code to simulate the full two-dimensional model. And you get a nice correspondence with the results of the full agent-based model. So you get this huddling metric goes down over time. We have this thermoneutral zone defined in the average body temperature of the group. And it brings out this clear prediction that the pup flow should spike at the critical temperature of this phase transition between huddling and not huddling. I'll speed up very quickly. But we're interested in the development of this system, right? I started off by saying I'm interested in how we can use this to understand development. What you can do is you can look at how some of these thermal properties are changing over time. So the dots here are based on experimental data. The lines are my model fits to those data. Quickly, in the interest of time, what we're looking at here is, over time, the amount of brown fat that the animals have per unit body mass decays exponentially over time. It's also been observed that the metabolic rate, so that's the basal metabolic rate, goes through this its own sort of phase transition where you get a spike in the basal metabolic rate at about postnatal day 8, which then tails off to establish the basal metabolic rate of the adult. There's a relationship between this exponential decay and this phase transition here. That relationship also depends on the weight of the animal in a way which can be modeled extremely simply in terms of those other parameters, the metabolic rate decay and the brown adipose fat tissue decay. And once you know those three things combined, you can make a prediction, which is the solid lines from my model, about the temperature preference, or the ambient temperature preference that the individual animal has. And so these data are from experiments performed at different days, where the animals were placed on a thermocline, which is hot on one side, cold on the other, and there's a gradient of heat between them. And then you just observe where does the animal go and stay, so what's its preferred temperature. What happens is, as the thermal physiology matures, the animals go from preferring a very warm temperature to preferring what they prefer as adults, which is about 31 degrees. Okay, this allows us to then plug those constraints into a huddling model, which is extended over time, over many weeks. And as you might expect, as the thermal physiology matures, the animals prefer warmth to start off with and then cooler towards the end. You run that through the huddling model and you look at the average huddle size. As you might expect, huddling is predicted to go down over time. Okay, and no surprise here. But what's interesting is that huddling isn't observed to go down over time at the same level. So how can we explain that? Well, what we can do is we can take this huddling model and we can imagine that each member of the group is able to sense, perhaps to smell, the other animals in the group, and on that basis is able to form a strength of association with the other animals in the group. Okay? And this is saying how that strength of association between pup A and pup B will change as a consequence of whether the prediction that A makes about whether it's going to be rewarded by coming into contact with B and the actual outcome of coming into contact with B. Okay, so this is something called the Rescorla-Wagner model from animal learning theory. It's the delta rule in neural networks, or very close to that. And so it's a very simple model of associative learning. And then what we can do is we can run that through the huddling model. Every time the two agents come into contact, if the consequence of that contact is advantageous, it brings their body temperature closer to the preferred temperature, then we increase the associative strength between them, otherwise we decrease it. And the consequence, when you look at huddling under those circumstances, where they're able to learn from interacting with each other, the consequence is that huddling levels remain constant. And the difference is that early huddling now is driven by this physiological need to huddle, whereas huddling later is not driven by the physiological need, but it's driven by the associative strength that the animals have made with one another. And they're making those associative strengths, they're huddling based on being reminded of positive experiences with one another, where positive experience means having experienced previous thermal reward by coming into contact with. Okay, so I'm almost finished. If we look in that system, we look at the associative strength that's made by one individual for, in this case, each of the other individuals in the huddle. Then this one individual will form strong associations with some, and weak associations with others, or even negative associations, all based on whether those initial experiences with one another were thermally rewarding or not. It's a very broad, bold claim, but for me this is a way of trying to think about how a social system can emerge from those basic ingredients, which is thermal physiology developing over time, some thermal consequences for the physiology of coming into contact with one another, and animal learning, basic kind of classical conditioning to predict whether those thermal consequences are going to be rewarding. Some animals will develop strong associations, other animals will develop weak associations, and it is a purely self-organising system. So I think this goes some way to explaining how a social system can emerge from those basic ingredients. Finally, I promise, the other direction that we've been taking this work is less abstract. Been imagining that little rat pups are controlled by this basic equation for turning left or right when they're too hot and too cold, which I've been describing, and allowing that to place constraints on the basic behaviour. And then we put a neural network, a self-organising map, in charge of learning the relationships between the sensory signals which are coming in and the consequences, whether the body temperature is getting better or worse as a consequence of making motor action. Put a neural network in charge of learning that relationship. And in this case, simulate things with a slightly more sophisticated 3D modelling approach called shape matching. We can at the start of this simulation, the animals are controlled by this subcortical hypothalamic circuitry which I've been describing. And what we're looking at, that's generating patterns of contact on the skin, which are then being fed into a self-organising map. We're looking at the pattern of sensory weights and motor output weights, which are being used to control the movements of the pup. We're looking at those change over time, and the top is showing the activity. And what I want you to take away from this is that if we simulate this process, the neural network learning the constraints which are imposed by the underlying hypothalamic control, then the neural network will learn a certain structure relationship between its motor weights and sensory weights, input weights and output weights, and that structure will depend on the parameterization of the environment. In this case, we've set the ambient temperature to be cold, so the hypothalamus is making them all squiggle together as much as they can to huddle, and that that introduces a set of correlations between the sensory inputs and the right motor outputs that should be performed as a response, and the network learns a particular, in this case, topographic mapping. If we do the same thing on a different temperature, that mapping turns out to be different. So run it when it's hot, hypothalamus is making these things all avoid one another. The pattern of correlations that are coming in between input from the skin and what was the right motor output to produce is different. And now these mappings become anti-aligned with one another. Do the same thing at intermediate temperature, and we can observe for different temperatures indicated by blue is cold to red is warm, the correlation between the sensory input weights to the map and the motor outputs to the map develop to be either positively correlated or negatively correlated as a consequence of the manipulation that we've made about the thermal environment. Okay, so the idea then is that the hypothalamus is governing these reactive behaviours, low-level responses to whether it's too hot or too cold, and that places constraints on the statistics of the developmental experience, which are then being modelled by this cortical circuitry, which will produce different mappings, systematically different mappings as a consequence of that manipulation of the environment. Okay, and this is just to show off that we have been using this 3D modelling approach to make nice wiggly rat pups, and there's a semi-serious objective, which is to then start to ask how the body morphology of the animal also influences the nature of these cortical maps. And I'll stop there with apologies for running over and leave up my take-home messages slide. The most important one is this: modelling behaviour can lead, modelling at the level of the behaviour can help us generate hypotheses about the lower level circuitry, which relates the physiology to the psychology. And yeah, that's where I'll leave it. Thank you.